All right, good afternoon, everybody. All right, so quizzes. Your Tuesday and Thursday group quizzes are marked. So you can pick your quiz up you can pick your quiz up in your lab. That's probably the easiest way to get them back to you. So the Tuesday group, you can pick yours up today. Unless you wrote an accommodated quiz, in which case those are at home, and I didn't bring them today. So I don't have the Tuesday accommodated ones here, but everybody else is here. From what I saw, the grades were quite good. So, yeah. All right, so today's lecture is about relationship between classes. So the classes we've implemented so far, pretty straightforward. You made a class, it had some primitive fields, and everything was not terribly complicated. As soon as you make a class where the fields are non-primitive type, a whole bunch of issues arise, and you have to consider these issues when creating your class. So a typical object-oriented program is made up of multiple interacting classes, and the relationship between those classes becomes important. Right? So you end up making classes that are created or built or have fields that are that are objects. Right? So you're now concerned about the structure of your classes. Right? How are classes built using other classes? Right? And in a program, any non-trivial program, your classes will interact with other classes. And so there's also behavior that you're interested in. We're not so interested in the behavior in this course. That's a subject for for a software engineering type course rather than this course. But there are ways to describe the behavior of your software as well. We're mostly concerned with structure. All right, so the weakest type, the weakest relationship between two classes is called dependency. So dependency models the uses relationship, right? So one class uses another class, right? So we say that a class X uses another class Y. If a class X uses another class Y, then we say X depends on Y, right? And it can also be the case that those two classes, Y uses X. So Y also depends on X, which means dependency can be a two-way relationship. Right? And you're going to see later on that there are relationships that are strictly one way, right? But dependency can be two-way. So when does a class use another class? Right? So X depends on Y if some object of type Y appears as a field of X. That's obvious, right? If X has a field whose type is Y, then it needs to use Y. Right? If any constructor or method has a parameter that takes in a Y object, then X uses Y. If any constructor or method internally makes a Y object or makes use of a Y object, then X uses Y. And of course, if any method returns a Y object, then obviously X uses Y. So you can show the dependency relationship in a UML class diagram. Right? So there's this class point2. Right, now, point2 implemented this method called toString, which returned a string representation of the point. So point2 uses the string class. And the way you show that on a UML class diagram is you connect the point2 class to the string class using a dashed arrow, a dashed line with an open arrow on the end. The line style and the arrow style are significant in UML class diagrams. We didn't talk about this class Vector2. But Vector2 is a companion class to point2. So point represents a location in space. Vector represents a direction. So Vector2 also implements toString, so it also depends on the string class. You can imagine that every class in the Java language depends on the string class, right? Because all classes have a toString method. Point2 also depends on the Vector2 class. So if you take 2 points and subtract them, you end up with a vector. Thus, point2 uses the Vector2 class. Association is a stronger form of dependency. So association models what's called the has-a relationship. Right? So if a class X has a field of type Y, then we say X has an association with Y. Right? And it can also be the case that Y has an association with X at the same time. Right? So association can also be two-way. Right? So you've got a class X, a class Y. Inside class X, you've got an object of type Y. And inside class Y, you've got an object of type X. Right? If that's the case, then you have if either one of those is the case, then you have an association. If you want to show an association relationship in UML, you draw a solid line between the two classes. So this lecture slide is from last term, and I didn't update it for this term. So last term, there was one of the assignments, they had to implement this class called ppm ASCII reader. So this is just a class that reads in a simple image format. It stores the image that it reads in inside of a simple image object. Right? So the structure of this class has one of these objects in it. You can show the multiplicity using a number on one of the classes. Right? So this diagram says a ppm ASCII reader has one simple image object. And this is a more complicated example of a UML class diagram. If you refer to the course notes, then this picture is in the course notes and it tells you where this picture comes from. It comes from a standard textbook in object-oriented programming. So this class diagram is trying to show the relationship between a class called show and a class called performer. So show is a class that represents like a musical show or some sort of Broadway show. Performer is just a performer in that show. Right? So a performer can be in the orchestra, or they can be in the cast, so one of the actors or actresses. What this picture is trying to show you is that a show has some performers, right? A show in the orchestra. A show has some performers in the cast, right? But the relationship is two-way. So if you're a performer, then you can be, or you can have, or you can belong to one or more shows, right, as a member of the orchestra, or you can be a member, a cast member of one or more shows. I guess 0 or more is the correct number. 0 or more shows. If you're a performer, you can also have a relationship with other performers. Right? So if you're a lead performer, right, then you may have 0 or more understudies. Right? And so that's what this relationship here is trying to show you in the diagram. So that's association. So dependency, one class uses another. Association, one class has a field whose type is of the other class. Aggregation and composition are stronger forms of association. Okay, so these are, both terms describe the has-a relationship, just like association does. Right? So it's a little bit confusing, because you have association, aggregation, and composition. They all mean has-a, but they all mean slightly different things. So an example of one of these types of relationships is the university. Right? So a university has a collection of departments. Right? The university is made up of a bunch of departments. And each department has a collection of professors. Right? The difference between aggregation and composition is that composition implies sole ownership. Right? So, let me back up one step here. So when you talk about aggregation and composition, normally you talk about the whole object and the part objects. So the whole object would be the university. The part objects would be the departments, right? University made up of departments, right? Department, that would be the whole object. Professors would be the part objects, right? So a department is made up of a bunch of professors. Composition implies ownership. So if the university disappears, then it would be the case that all departments would also disappear, right? So the university is an organization of departments. A department can't exist without a university. So if the whole object disappears, then all of its parts also disappear. Right? Now the relationship between a university would be a composition of departments. Aggregation does not imply ownership. So for example, if a department disappears in the university, then it's not necessarily the case that the professors also disappear. Right? A professor might be appointed in more than one department or in more than one faculty. Right? They may be appointed at more than one university. So the fact that a department disappears does not mean that the professors also automatically disappear. Right? So in an aggregation, if the whole object goes away, it's not necessarily the case that the part objects also go away. Right? So in this case, a department would be an aggregation of professors. Right? Now, what's the difference between aggregation? So this looks exactly the same. Aggregation looks exactly the same as association. And many people will argue that, in fact, they are the same thing. The only distinction between the two is that aggregation and composition, these are both one-way relationships, whereas association is can be a two-way relationship. So in this case here, a department is made up of professors, right? But a professor is not made up of a bunch of departments, right? So in this case, this particular relationship, the way I've written it, it's strictly one way. And so that's the difference between aggregation and association. All right, so here's a concrete example of an aggregation relationship. So if you look in many standard textbooks, you'll see a class that appears like person or student or employee or something like that. Right? So here I'm just going to say a person has a name and they have a birth date. Right? They could have a bunch of other things too, but for simplicity, let's just keep it with these two. Right? So for the name, I'm going to represent the name of the string. For the birth date, I'm going to use this object called date. So date is Java util.date, which represents time. Right? So we've got a field of type string and a field of type date, right? So they're both reference type fields. And so the relationship between the name and birth date object to the person object is important or significant. Here's our constructor for the person class. So it takes in a name and it takes in a birth date, and we simply write this name equals name and this birth date equals birth date. Right? Now remember what this does in Java. Right? So this says that this.name refers to the same object as the parameter name. Right? And it also says this birth date refers to the same date object as the birth date object, as the birth date parameter. Right? So you can see immediately that the person doesn't own its name or its birth date. Right there, those two lines there clearly indicate that the person object is sharing its fields with someone else, right? Whoever called the constructor. Right? If you ask the person for their name, they simply return this.name, and if you ask the person for their birth date, they simply return this.birth date. Right? And so this is exactly what you would have implemented if all your fields were primitive. Right? This is exactly the same code that you would write, so there's nothing really complicated here. Right? So that example right there is an example of a class that uses aggregation. Right? The constructor does not make a new copy of the name or birth date objects passed to it. Right? And so what does that mean? It means that the name and birth date objects are shared with whoever called the constructor. So I'm calling that the client, right? But that's just whoever called the constructor. What does that mean? It means both the caller and the person object are holding references to the exact same string and the exact same date object. Right? So for example, if someone writes the following code, right, so they have the string Billy Bob, and they have this date here, which is March 26, 1991. If they make a person object using S and D, then what happens in memory is the following. Right? So there's one string object, right? That's the name Billy Bob. There's one date object, which is the date March 26, 1991. Right? The caller has a reference to the string and the date. Right? So their string reference is referring to that object here. The person object also has a reference to that exact same string object. Right? And similarly, the caller has a reference to that date object, and the person object also has a reference to that date object. Right? So these two objects here are shared between the caller and the person object. Right? Neither one owns or has exclusive ownership over those objects. So what happens if someone changes the date? Right? So it turns out date is mutable. So you can change the time that a date object represents. So you can set the year, the month, the date, the hour, the minute, and the second, I think. And so we changed the date to November 3rd, 1995. Right? And so we're going to use the date object D here to change the date. If you ask the person, what is your birth date? Right? It suddenly changes from March 26th to November 3rd, 1995. Right? And so that shows you what happens. You can change the birth date of a person without asking the person object directly. Right? As long as you have a reference to their date object, all you have to do is change that date object, and then the person object sees this modified date. Right, so that actually prints out midnight on, or sorry, midnight in the morning of Friday, November 3rd. Right. So because the date object is shared between the caller and the person, right, the caller can modify the date using D, right, and the person object P sees the modified birth date. Similarly, right, the person instance P can modify the date, and now the caller sees the modified date as well. Right. Oops, sorry. But what about the name? Right? So the name, though, is implemented using a string, right? And strings are immutable. So it doesn't matter if we're sharing the string objects, right? Because no one can change that string object. Right? So the caller can't change the string, and the person object can't change the string. Right? And so what does that mean? It means it makes your life a lot easier when you try to debug your code. Right? So if you have immutable objects, if you can afford to use immutable objects, then they make very nice building blocks for making other objects. Right? You never have to worry about the string changing, so you don't care about its state. Right? It's always the same. And so you can freely share those objects, right, without worrying that they're going to change on you. Okay, so to draw an aggregation relationship using UML, the whole object gets these little diamonds attached to it. Right? So the person object is an aggregation of one date, right? And the person object is an aggregation of one string. Right? So open diamonds indicate aggregation. The diamonds go on the whole object, not the part objects. Right? So this picture is basically saying a person is made up of one date and a person is made up of one string. Or a person has one date and person has one string. Right? It all means the same thing. Oh, notice that the relationship going the other way is not true, right? A date object is not made up of, or does not have one person object, right? And so that's why this is aggregation and not association here, right? Similarly, a string does not have a reference to a person object, right? This is the bouncing ball example that I showed you early in class. So that bouncing ball is just, I think it's a class called projectile. Might be called ball, I don't remember. The position of the ball is represented using a point2 object. The velocity of the ball is represented using a vector2 object. Right? So a projectile, in this example, has one point2 object that represents its position, right? And a projectile has one vector2 object that represents its velocity. Right? Implementing this thing is pretty straightforward. Right? So here's our class projectile. Right? It has one point2 object and one vector2 object, right? Representing the position and velocity of the ball. No argument constructor just sets the position and velocity to 0, 0, and 0, 0. Right? So it's a ball at the origin that's not moving. Get position, well, it just returns this dot. That should be POS, and that should be VEL. Right? So these two methods here, they simply return references to the internal fields. Set position takes in a new point, or takes in a point P, and then simply sets the position to be equal to P. Right? So its position object is the same object as P now. Right? And then it returns the old position. Set velocity is exactly the same thing. Right? Takes in a vector V, and then says that this dot VEL is the same object as V. Right? And then returns the old velocity. Move just implements the simple projectile equations of motion, right? So this isn't actually important, right? Although you guys could manage this because you've taken your first year physics course. So implementing projectile is pretty straightforward, right? The fact that the position and the velocity of the ball are objects doesn't really matter here, right? When you look at the code, right? So for get position, well, we just return a field. Get velocity, you just return a field. Set position, well, you just set a field, right? And set velocity, you just set a field, right? So there's not really any different than if the fields had been primitive, right? So the fields, they're just references to existing objects, right? The accessor methods, they simply return a reference to the internal point and vector, right? And the mutator methods simply set the internal point and vector to the incoming objects, right? And so those fields that are inside the projectile class, most of the time, they're just aliases or different names for some other object, right? And so we're called, you often will see these called aliases, right? The fields aren't unique to each point, to the projectile, right? Oh, sorry, they don't refer to unique objects for each projectile, right? They probably, in most cases, refer to some other point or vector belonging, that originated from somewhere else. Right? So to make a projectile, you can do this. You can do the following, right? So make a point, make a vector, make a projectile, and then set the position and the velocity of the projectile. That should be VEL, sorry, to POS and VEL, right? And away you go. Right? If you want a memory diagram of that, it looks like the following. Right? So there's your point object, and there's your vector object. Right? The caller has a reference to that point. Right? The projectile also has a reference to that point. Right? So nobody owns this particular point 2 object. The caller has a reference to that vector object, and the projectile has a reference to that vector object. So no one has sole ownership over that vector object. Right? The caller has a reference to the projectile object. Okay, so if we ask the ball, what is your position? Right? Then the ball simply returns a reference to that object right here. And so is that reference, or is that object, the exact same object as the caller's object? And the answer is yes, right? They're both that, right? They're both that one object that's right there. Right? So if you use equals equals to ask are they the same object, you get back true, right? Because there's only one point object in this entire program. Right? So is it true? Well, what does equal equals do? It just looks at that value and that value there. If they're the same, then the answer is true. If they're different, then the answer is false. Right? So that's what equals equals always does. It just looks at the value that's stored here and the value that's stored here. It doesn't matter if it's a primitive type or a reference type. Right? It's the exact same comparison that's made. Okay, so if the caller takes their point, right, and changes their point, right, to minus 99 and minus 22, right, you don't even have to ask the ball for its position. Right? So here we asked it for its position. You don't have to ask for its position anymore, or again, right? If you simply print out that object right there, you get the changed object, right? You get back minus 99 and minus 22, right? Why? Because that thing there is just a reference to that object there, right? So you don't even have to ask the ball for its position. It's changed, right? So I don't have to run that line of code again, right? It really will change right there when you print it out. Right? Why? Because, well, it's all just references to the same point object, right? Which is right here, right? So as soon as you change that point object, right, the projectile has a reference to that thing there. Oh, ball position now is also a reference to that object there, right? Okay, so if somebody gets a reference to the position or velocity of the ball, right, then whoever gets that reference can simply change the position or the velocity without asking the projectile, right? Just like we did here, right? So in other words, the projectile is not under control, it does not have sole control over its position or velocity, right? Somebody else can reach in and change its internal fields. Now, you might think that's weird, right? So you might say, well, why would I ever use aggregation, right? And it's not a flaw of aggregation, right? So there's nothing broken here, right? It's simply a consequence of choosing to use aggregation in this example. Right? Now, if you really want the ball to only change position if you ask it to, right? Now you have to do something else, right? And the something else becomes considerably more complicated, right? The something else you have to do is composition, right? So this is the stronger form of association, right? So recall that if an object of type, an object of type X is composed of an object of type Y, what does that mean? Right? It means X has a Y, right? So it's still association. But it also means that X owns the Y, right? X and only X owns that Y. Right? In other words, when you implement a composition, what you have to ensure is that the X object always has exclusive access to its Y object. Right? It will never hand out a reference to its internal Y object. Right? So what does this mean? It means that if you have a constructor, right, that takes in a Y object, right, you can't simply say this dot Y equals Y. Right? You have to make a copy of the Y object and then set your field to refer to the new copy. If you have a method that returns one of your internal fields, then you can't return the internal field. You have to return a copy of the internal field. Right? If you have a mutator method that changes one of your internal fields to a new Y object, or to a passed-in Y object, then you have to make a copy of the incoming Y object. Right? All of those copies, these are all called defensive copies. Right? They're defensive because they're needed to ensure that the X object has exclusive access to its Y object. Okay, so what happens if you have a no arguments constructor, which I'm calling default constructor here, right? So if you have a no argument constructor and you have a field of type Y, then obviously you have to make a new Y object inside the constructor. Right? That's not actually a defensive copy, but anyway. This is where the defensive copy actually comes in. Okay, so you have a constructor X that takes in a Y object. Right? The first thing you have to do is you have to make a copy of that incoming Y object. Right? So there's your defensive copy right there. Here I'm using a copy constructor that belongs to the class Y. If you don't have a copy constructor, your life becomes a little more complicated here. If there are conditions, preconditions on the value of Y, you now have to validate the copied object. Right? So I'm calling the validation check Y, because I don't know, this is just a generic example, so I don't know what you would actually write here. Right? But imagine you have some method that tests the state of the Y object. Right? If it's valid, then nothing happens. If it's invalid, it throws an exception. Right? Only once you're sure that the copy is fine or suitable for your purposes can you write this Y equals copy Y. Right? If there's no preconditions on Y, then you don't need the check, right? But you still need the copy. So why do you need that copy? Right? In order to ensure that X has exclusive access to Y. Right? If you write this, which is what you would have written if you're implementing an aggregation, right? Then what happens? This Y and Y are the same object. Right? You're now sharing your internal Y object with whoever just called the constructor. Right? When this happens, right, that's called a privacy leak. Right? So whenever a class or an object inadvertently shares one of its internal fields, that's called a privacy leak. Okay, what happens if you have a copy constructor? Right? So I have a copy constructor for X. It copies another X object. Right? What do you have to do? You have to make sure that when you copy the other object, you copy its other Y object. Right? So you have to make a new defensive copy of the other object's Y object. Right? Assuming there's a getY method. It doesn't matter if there's getY or not. Right? You have access to the private stuff of other anyway. So you could just write other.y there. Right? But you need that defensive copy. If you write the following, right, this Y equals other.y, what have you said? You're saying that your Y object is the same object as the other object's Y object. Right? So now you have two X objects that are sharing the same Y object. Right? Neither has exclusive access to its internal Y. Right? What ends up happening is every X object created with a copy constructor ends up sharing its Y object. Right? If one X object modifies its Y object, all your other X objects end up with a modified Y object, which probably isn't what you want if you're implementing composition. Right? So again, that's a privacy leak. Right? we are inadvertently sharing one of our internal fields with some other object. Okay, so the projectile class, how do you implement its copy constructor? If you want to copy another projectile, whoops, right? What do you have to do, right? So whatever you do, you don't write the following, right? It's not other position, and it's not other velocity. Oh, sorry. Right? If you do that, you've done aggregation, right? Your projectile now shares its, has the same position and velocity as the other object, right? You have to make a new object. And similarly here. Right? So now your projectile object has its own independent position and velocity. Right? Okay. Suppose you have an accessor method that returns one of your your y object. Right? Oops. Where'd it go? Did it? Okay. So if you have an accessor method that returns one of its internal y object, you cannot write return this dot y. Right? So never return a reference to one of your fields. Always return a copy to one of your fields. Right? So make a new y object, copying your internal y object, and return a reference to that object. Right? If you don't, right? So if you write that, what happens? You've just shared your y object with somebody else, right? And you no longer have exclusive access to it. Right? So again, you end up with a privacy leak. Right? And finally, Okay, so this should be projectile, right? So how do you implement get position? Return new point 2, this dot position. Right? How do you implement get velocity? Return new vector2, this dot velocity. And finally, the last case, if you have a method that changes the y object belonging to your object, right? So it takes in a y, and it changes its internal y, right? Then you have to do the same thing that the constructor does. First thing you do is you copy the incoming object. You validate it if you have to, and then only after the validation succeeds do you assign the copied object to your internal y field. If you don't, so if you write this y equals y, right, you're saying your y object is the same as that y object. Right? You're now sharing the internal y object with someone else. Right? So again, that leads to a privacy leak. Okay, so how do you implement set position? This position equals new point to this position. How do you implement get a set velocity? This velocity equals new vector2 velocity. Right? Make a new object that copies the incoming object. Okay, so the question is why don't you always use composition? Right? The answer hopefully is obvious. Right? There's all these copies flying around all over the place. Right? So whenever someone's calling a method or calling a constructor, right, there is the possibility that a defensive copy is being made. Right? And what does that mean? It means it takes time to make the copy, and it takes additional memory to make the copy. Right? If the copies are temporary, then it also takes time to get rid of the copies when they're no longer needed. Right? So the bouncing ball program, that's basically moving the ball every 25 milliseconds. Right? So if you're using composition instead of aggregation in the bouncing ball example, right, then you're making basically 40 0.2 objects every second just to move the ball. Right? Whereas in aggregation, you're never making a new 0.2 object to move the ball. Right? You just change the internal point. And it moves. Right? So you pay this huge price for making these these defensive copies. Right? And so that's why you don't use composition if you don't have to. Okay, any questions so far on dependency, association, aggregation, or composition? Yes?
Just the bit about creating new ones.
Yep. So there's something in the Java virtual machine has what's called a garbage collector. And so the garbage collector runs, well, whenever the virtual machine decides it should run. And it looks for objects that have no references to them. Right? So if it finds an object with no reference to them, it can clear them from memory. Okay, so, yep, sorry.
Can you just go over why composition is expensive?
Yeah, it's all of these defensive copies that have to be made, right? Every time you make a copy of something, there's a price that you have to pay, right? It's memory and time that you end up paying. If the object is big or is hard to copy, then you can pay a really big price for copying them all the time, right? So you generally want to avoid copying stuff unnecessarily. All right, so you would like to avoid, you probably in most cases want to avoid composition, but there are many situations when you cannot, right? So if your class has an invariant on some of your fields, then it's almost certainly the case that you have to use composition. Right, so remember what an invariant is on a class, right? It's some property of the state of the object that's always true, right? So the constructors establish the invariant when the object is created. Every public method has to make sure that the invariant is true when it finishes returning. Okay, so we need an example of a class that has some invariants. So I'm going to use an example that comes from the effective Java book. So it's a period class. It represents a period of time, right? So something like a time slot on your time schedule, on your class schedule. Right? So every period of time has a start time and an end time, right? So what's the invariant here? Well, the end time always comes after the start time. Right? So in our case, we're always going to make sure it's strictly after the start time. Right? And so that becomes your class invariant. So how do we implement the period class? Well, I need some way to record time. So I'm going to use a date object. Right? So our period object has a date that represents the starting time of the period, and it has a second date that represents the end time of the period. Right? And we need to make sure that the start time always comes before the end time. So our period class is going to be a composition of two date objects. Right? So a solid diamond indicates a composition. All right, so before we proceed with this example, we have to, if we're implementing a composition, we know that we're making copies. So you need to know how to copy a date. Date doesn't have a copy constructor. Right? So instead what you have to do is you have to call this method called getTime on your date object. And then you can pass that result to the date constructor, and that will make a copy of the object D. Right? So whenever you see date D get time, that's the reason why. There's no copy constructor. Okay, so our class period has a start time and an end time. They're both date objects. Right? The important things to remember here are these are two, the date is a reference type, and it's mutable. So I'm going to make a constructor, right? Takes in a start time and an end time, right? We're going to check, is the start time, does it come after the end time, right? So start compare to end. If it's greater than 0, that means that the start is after end, right? So we'll throw an exception to indicate that this is illegal, right? And now we're going to write this start equals start and this end equals end. So what happens in this case? So I'm going to make I have my start time. New date makes a time that's equal to the current time. Right? I have an end time. So I'm going to get the starts time, and I'm going to add 10,000 milliseconds to it. So this is 10 seconds after the start time. Right? So my start time really does come before the end time. And then I'm going to make a new object using that, using the start and end. Right? So if I write that line of code, and if the constructor is implemented this way, right, you can easily break the class invariant without going through the period object P. Right? So in order to break the class invariant, you need to set the end time or the end time to be before the start time, or the start time to come after the end time. Right? So what do these do? So end set time to end get time, that doesn't change end, so that doesn't break it. End get time plus 10,000 is 10 seconds after the end time. So that doesn't break it either. Right? Start set time to end get time minus 1 sets the start time to 1 millisecond before the end time, which is still fine. Right? But if you set the end time to the start time, that breaks the invariant, right? Because the end time and the start time are now the same. You've broken the class invariant, and you're not even inside the class itself. Right? So if you implement the constructor this way, there's no way that the period class can guarantee that its invariant is always true, right? Which more or less makes the period class useless. Or it makes the invariant useless anyway. Right? So what's the solution? You have to make sure that that start time and that end time, when you take them into the class, that you copy them. You don't use them as they are. Right? So it's straightforward. Make your copy of your 2 times. Right? Compare your copied times. And then only after the copies, only after you've done your validation, right, can you set this start to be equal to the copy and the end time to be equal to the copy. Right? Once you've done that, you've ensured that your start time really is a new distinct object from that, and you've ensured that the end time is a new distinct object from that. Right? So now your period really does have its own independent start and end time. Here's a copy constructor for the period class. Right? So if you're implementing aggregation, you would just write this start equals other start, this end equals other end. Right? Right? Sorry. What happens if you do that? Well, you're now sharing your start and end time with another period object. Right? If the other period object changes its start and end time, then this period object also sees a changed start and end time. Right? So what do? Make a copy. Right? So new date here, and away you go. What happens with these get start and get end methods? Right? So if you just return the start time and the end time, right, you've just handed somebody a reference to your internal start time and a reference to your internal end time. Right? Again, both privacy leaks. Right? Don't do that. Right? Make a copy, return the copy. Right? And finally, if you have I think it's finally, yeah. If you have a method that sets one of the 2 times, so here's we're setting the start time. Right? Now, we have a class invariant, so we actually check, is the new start, is it before the current end time? Right? If it is, then I'm going to set the start time to equal the new start time, and I'm going to set OK to true, and then I'm going to return OK. Right? Otherwise, we return false. Right? What happens if you do this? Well, your start time object is the same object as that object. Right? So you're now sharing your start time object with whoever called the method. Right? Make sure you make the copy. Right? So make the copy first. Check that the copy is valid. Right? Then only when you're sure that the copy is valid can you go ahead and assign your start time to be equal to the copy. Okay, so in summary, a privacy leak occurs when your class exposes a reference to a non-public field that is not primitive and not immutable. Right? It doesn't matter if you expose a reference to an immutable field. Right? So for example, if your class has a string, then it doesn't matter if you use composition. Well, you never use composition if you have a string. Right? Because there's no point in copying the string. It can't be changed anyway. Right? If it's primitive, it also doesn't matter. Right? Because you can never share a primitive value with somebody else in Java. So if you have a class that is a composition, right? So x is a composition of a y, right? Then you can never write any of these. If you ever write any of those, you've got a problem. Right? Instead, oops, do I have it anywhere? No, right? Instead, this y equals new y, right? This y equals new y. Return new, this y, right? And this y equals new y here, right? Make sure you make your defensive copies. Okay, so what happens if you have a privacy leak? So a privacy leak allows some other object to control the state of your object that leaked the field. Right? And so what does that mean? Right? right? If the state of the object can become inconsistent, right? So for example, if you have a credit card class and it exposes a reference to its internal date, right? Then to its internal expiry date, then somebody can just go ahead and change the expiry date. You would never implement credit card this way anyway. Right? If you are implementing a composition and you have a privacy leak, suddenly all of your invariants go out the window. You don't have any anymore because you don't control the state of the object. Right? So if period exposes a reference to one of its two date objects, right, then the period class can no longer guarantee that the start time is always before the end time. And finally, if you have a privacy leak, composition becomes broken, right? Because the object no longer owns or has exclusive access to its internal field. So what does that mean? So that means when the whole object dies, its parts may not go away with it, right? And that's what's supposed to happen in a composition, right? So in a composition, when the whole object goes away, all of its individual parts should go away as well, right? Because the whole object is supposed to have exclusive ownership over its parts. Okay. So if you want to make an immutable class, then you have to pay attention to this whole business of composition. Right? So if you wanted to make a class like string, then you have to make sure the following 5 things are all true. Right? So first of all, you're not going to provide a method that lets someone change the state of the object. Right? So no mutator methods. We'll skip number 2 for now. Right? You'll probably want to make all your fields final. Right? The reason for doing that is if you make your fields final inside the class, then you're sure that you're only going to set each field exactly once. Right? You will never accidentally set it a second time. You have to make your fields private, right? Otherwise people can see into the class, and if they're not final, they can go reach in and change those values. Right? And then finally, if you have any methods that can expose a reference to one of your fields, then you have to make sure that you use composition to not expose those fields. Right? Step 2 is a subject of a lecture in a few days. I guess we should stop there and mosey on over to the lab if we have one. So we'll talk about what happens when you have composition with a collection in the next class.